Hello and welcome to another video. In this video, we will see about the basics of linear algebra, which will be helpful for understanding the concepts of control engineering. So in this video and the next video, we will try to cover the fundamental linear algebra concepts that are essential for control engineering. So what is linear algebra? Linear algebra is a branch of mathematics that deals with vectors, vector spaces, matrices, and their operations, or linear transformations. So all these concepts will be used in control engineering. Why is it important in control engineering? We use these linear algebra concepts to solve a system of equations. Many engineering problems which involve this solution of Ax equal to B form. We will say more about this in the later sections. Here we have the unknown variables here. So we try to solve that by using linear algebra, solve this type of equations by using linear algebra. And another importance of linear algebra in control engineering is due to the state space representation. So control systems are often expressed in matrix form to analyze the stability and the performance. The state space representation is an important way of representing a system. And this linear algebra will help us to do all the modifications, manipulations to analyze the stability and the performance of systems, which is represented in state space form. We also use the eigenvalues and eigenvectors, which is in linear algebra, used for the stability analysis of dynamical system. Suppose a simple system is represented as 2x plus 3y equal to 5 and 4x plus 6y equal to 10. As you can see, the second equation is just a multiplication factor of the first equation. So when you multiply the first equation twice, you get the second equation. So the coefficient matrix of this system is A equal to 2, 3 in the first row and 4, 6 in the second row. Since row 2 is a multiple of row 1, the system is dependent. Means there is no unique solution that exists for this set of equations or the system representation. So there are multiple solutions possible for this set of set of equations. So similarly, we can represent a system of equations. A physical system can be represented by a set of equations that can be transformed into matrices, and then we can analyze about the system. Now the applications in control engineering we use mainly for modeling the dynamical systems like robotic arm, aircraft, electrical circuits can be described using the linear differential equations, which are solved using matrix methods. We can also analyze the stability of a system. Engineers use eigenvalues to determine if a system will remain stable over time. As I mentioned earlier, we will also use the state space representation. Instead of using transfer functions, state space model uses matrices to represent the system dynamics. We will see an example. The mass spring damper system, that system follows the equation mx double dot px dot plus kx equal to f. F is the input force. In our video which explained about the mechanical systems, we had seen such kind of systems. This second order system can be represented like this. x1 dot equal to x1 dot x2 dot equal to 0 1 minus k by m minus c by m x1 x2 plus 0 1 by m f. So this matrix representation is of the form x dot is equal to ax plus bu. That gives a relation between the input and the states. So this is the rate of change of the system. So for a dynamical system, the relation with the input and the system states are normally represented by this equation. So this is how we transform a system model, a differential equation, into matrices, and then we analyze these matrices to tell about the system, how the system behaves, how the input influences the system, all those. Some of the basic elements of a linear algebra are scalars, vectors, and matrices. A scalar is a single number, like for example mass it is 5 kilogram, 10 kilogram, or a temperature of a system, 300 Kelvin, 250 Kelvin. So those are scalar elements or a single number. Vector is an ordered list of numbers, usually written as column, like p equal to 3, 2, minus 1. 3, 2, minus 1 are the elements of that vector, and v is the vector. These are normally used to represent forces, velocities, state variables, etc. A matrix is a rectangular array of numbers. It has rows and columns. So these are rows and these are columns. These are mainly used in the state space equations to describe the system behavior. Say, for example, this is a rotation matrix. So it describes a robotic arm rotated by theta degrees, uses this rotation matrix. Similarly, the information can be understood in terms of matrices, so matrix manipulations. Vector spaces and subspaces. A vector space is a set of vectors that satisfies closed under addition. Adding two vectors in the space results in another vector in the space. Closed under scalar multiplication. Multiplying a vector by a scalar results in another vector in the space. We will see an example. 2D plane as a vector space. So this is two-dimensional given that x and y belongs to the real numbers. This represents a vector space. Subspace is a smaller vector space inside a larger one. So the entire 2D plane can be a vector space, and subspace are smaller spaces within a vector space. The x and y axis are used to represent a plane, and a subspace can be a set of all points on the x-axis. Also, in a 3D space, the set of all points along the x-axis forms a subspace. Linear independence and basis. A set of vector is linearly independent if none can be written as a combination of other. Earlier in this video, we have seen two equations which were dependent on each other. Now, linearly independent equations cannot be written as a combination of others. We will see an example. The vectors 1, 0 and 0, 1. Those are independent vectors because we cannot write this vector as a combination of this vector. Whereas we can write this as a combination of this and vice versa. And a basis is a minimal set of linearly independent vectors that spans an entire space. The standard basis of a 2D space is, so this is a standard basis for a 2D space. Why is it important? The number of basis vectors define the dimension of a system and helps us in controllability analysis. When we see in the perspective of the control engineering, this basis vectors are a very important concept. Matrix operations. These are addition, multiplication, transpositions. All these are basic matrix operations. They are used to combine system equations, and transposition are useful for symmetric properties. And there are some special kind of matrices like identity matrix or a diagonal matrix. Identity matrix can act as a neutral elements in multiplication, and diagonal matrices simplify the calculations. So addition operation, we will see an example A plus B, where this is A matrix and this is B matrix. And each element of A matrix and each element of B matrix are added to get this resultant matrix. So 2 plus 6 is 8, 3 plus 7 is 10, 4 plus 8 is 12. In matrix multiplication, when we multiply A matrix 1, 2, 3, 4 with the B matrix 2, 0, 1, 3, we get this as a resultant matrix. So in multiplication, we multiply first element with this first element 1 into 2 plus 2 into 1 to get the first element, that is 4. Similarly, we will multiply this first row with the second column to get this second element. So 1 into 0 plus 2 into 3, we get 6. Similarly, to get the second element in the first element in the second row, we multiply 3 into 2 plus 4 into 1 to get 10. Similarly, the second row and second column is multiplied to get the final element, fourth element in this resultant matrix. 3 into 0 plus 4 into 3, we get 12. Why is it important? It is used in the representation of system dynamics. In control engineering, we represent a system, dynamical system, as x dot equal to ax plus bu, where x is the states and u is the input. We use this matrix manipulation, multiplication, to compute the system response. Determinants and inverse of a matrix are very important concepts. A determinant is calculated by, suppose we have a matrix with elements A, small letter A, B, C, and D. And the determinant of A is represented like this. A multiplied with D minus B multiplied with C. So A is the element multiplied with the D element minus B element multiplied with the C element. A matrix is singular if its determinant is 0 and is non-singular if its determinant is not equal to 0. And how to compute an inverse of a matrix? So we first have to calculate the determinant of that matrix, and if it is non-zero, only then we can calculate the inverse of a matrix. A matrix is invertible if and only if this determinant is not equal to 0. We'll see also in later what happens when the determinant is equal to 0. Still we will be able to approximately calculate this inverse, but here to begin with we will assume that the determinant of A is not equal to 0, and how to calculate A inverse. So we will take 1 by determinant of A and D minus B minus C and A. So for larger matrices, we use step-by-step method to calculate the determinant. For a 2 by 2 matrix, this is the step to calculate the inverse of a matrix. What is a rank of a matrix? A rank of a matrix is the number of independent rows or columns. We have seen in the previous slides what is independent vectors. So in a matrix, if there are independent rows or independent columns, then the rank of a matrix is said to be full rank. Say for example, A equal to 1, 2, 3, and 6. Since the row 2 is a multiple of row 1, the rank of A is 1. If suppose we had two independent columns or two independent rows, then the rank would have been 2. And it is said to be full rank. So the rank of a matrix is the number of independent rows or columns. So it gives us a relation with system solvability. So it helps us, this rank will help us in calculating the controllability or observability, etc. from the control perspective. A system of linear equations are represented as Ax equal to B. Now there are many methods of solving the system of linear equations in linear algebra. Some of them are Gaussian elimination or matrix inversion, LU decomposition. So we will see some of them while discussing the solutions of system of linear equations. So why is it important for control systems? So many engineering problems reduces to solving Ax equal to B. Sorry, we will try to solve for X. In this system of equations, Ax equal to B, we will try to solve for X. And if A is invertible, we will try to solve for X as A inverse multiplied with B. B sometimes is a vector. If X is a vector, B is a vector, and A is a matrix, we will find the A inverse and then multiply with B to solve for X. And if suppose A is singular, that is nothing but determinant of A equal to 0, then no unique solution exists for X. So we will see more basic concepts of linear algebra in next video, like eigenvalues, eigenvectors, etc. Thank you.